So hi, this is Sathish Kumar from EEE department. I'm going to teach subject DC machines and transformer on topic of DC generators. Okay, then we'll start today topic. First of all, what is generator? A generator, it is a DC generator or AC generator. AC generator is also called as a alternator. So coming to in our subject, we are discussed only mainly DC generator. DC generator is an electrical machine which is converts the mechanical energy into direct current electricity. That is the function of DC generator. Then the principle is different, function is different for generator. So what I told now, that is the function. Is the function of generator is converts the mechanical energy into electrical energy. That means it direct current electricity. This energy conversion is based on the principle of production of dynamically induced EMF. Principle of production of dynamically induced EMF means according to dynamo. According to dynamo principle, the electromechanical energy conversion process is there in case of the DC generator. That first, before the principle of production of dynamically induced EMF discussion, before that, we need to discuss electromechanical energy conversion process. That I will discuss now. This is mainly, we'll discuss here energy flow in electromechanical energy conversion device as a generator. In case of the generator, for example, I am giving here mechanical system providing a input. Mechanical system I am giving providing as a input. Now that mechanical providing system input that will be connected to the coupling field. Means I am using here one coupling. That coupling field is there. From that coupling field to, that is the output, whatever the output as a function of the DC generator is there. That is the electrical system providing is a output. So coming to, you can observe here. So this is the mechanical system providing is a as an input. Now in between the mechanical system providing as an input to the coupling field, I am getting the mechanical losses mainly. I am getting the mechanical losses. So this is the mechanical losses I am getting here, and the gross mechanical input is equal to integration of T into omega dt over integration of F into V into dt, where T is the torque, W is the omega is the angular velocity, and F is the force of the conductor, V is the velocity of the conductor. So now, this is the gross mechanical input I am giving to the generator input. Now, so in between the mechanical system providing input to the coupling field, I am getting the mechanical losses. After mechanical losses, I am getting here net mechanical input available. Means mechanical system providing input, whatever the input I am providing here, minus mechanical losses if you are doing, then I am getting the net mechanical input available here at the coupling field. Okay, that is I am calling here integration of F dash V dt comma integration of F of omega dt. Now this coupling is heating due to of the coupling field losses. Okay, then due to of that heat, I am getting the another losses here, that is the coupling field losses I am getting. So this, according to this coupling field losses, is minus from the net mechanical input available to the coupling field. Then I am getting the gross electrical output available at this point. That gross electrical output available at this point is called as a integration of EI into dt. So after that also I am getting the electrical losses. That electrical losses is copper and iron losses. Okay, then copper and iron losses is there. So then I am again subtracting from this gross electrical output available from the electrical losses. Then I am getting the net electrical output, that is an integration of Vi into dt, that is the electrical output I am getting here. So from electrical losses, subtracting from the gross electrical output available, then I am getting the net electrical output here. So this is the total process I am calling, energy flow in electromechanical energy conversion device as a generator. According to this process only, DC generator principle will be there and the function also is there. Now here, for a generator, input is a mechanical energy, but entire input cannot reach to the coupling field for the conversion because there is a mechanical losses is there. So that's why this mechanical losses is subtracted from the gross mechanical input. Then I am getting the net mechanical input available at the coupling field. So the part of get lost in the form of friction and windage losses. This mechanical losses I am calling friction and windage losses. So the mechanical input is converted to electrical by the device via coupling field, but net output cannot be equal to the converted electrical energy as same part of its lost here. Okay, so that's why that is in the form of the electrical losses. That electrical losses I am calling as a copper and iron losses. So this is the energy flow in electromechanical energy conversion as a device, as a generator. Okay, now according to the generator function, in electrical machine will convert the mechanical energy input into the direct current electricity. So this energy conversion is based on the principle of production of dynamically induced EMF according to the electromechanical energy conversion process. Now here, according to the principle of the generator, here we'll discuss now. According to Faraday's law of electromagnetic induction. This Faraday's law of electromagnetic induction depends on the Faraday's first law and as well as the Faraday's second law. Faraday's first law means a current carrying conductor, if you are placed in the magnetic field, then I am getting the induced EMF. Which induced EMF? That is dynamically induced EMF I am getting. So means whenever the current carrying conductor is placed in the magnetic field, we are getting the two types of the induced EMF here. One is the dynamically induced EMF as well as the statically induced EMF. Then you will get the one doubt here. What is the difference between the dynamically induced EMF and statically induced EMF? Coming to dynamically induced EMF, according to the Faraday's first law, I am taking here a current carrying conductor. If you are placed in the magnetic field, then we are getting the induced EMF. Means here the conductor is rotating or otherwise the magnetic field will be rotating. So if both will be rotate, then we are not getting the induced EMF. If both will be constant, also there is no induction process in between the conductor and the magnetic field. So that's why any one will be rotate, then only the induction process will be going on in between the conductor as well as the magnetic field. Then only we are getting the induced EMF. So will conductor is rotating and the magnetic field will be constant, then the induction process will be going on in between the conductor and as well as the magnetic field. Then we are getting the magnetic field. Then we are getting the induced EMF. That induced EMF I am calling as a dynamically induced EMF. If magnetic field will be rotating and the conductor is constant, then also the induction process is there in between the conductor and the magnetic field. Then we are getting the induced EMF. That induced EMF I am calling as a statically induced EMF. So in case of the DC generator, the principle will be depends on the dynamically induced EMF. So according to Faraday's law of electromagnetic induction, whenever a conductor is placed in a varying magnetic field or a conductor is moved in a magnetic field and EMF is EMF is nothing but electromotive force gets induced in the conductor. So the magnitude of induced EMF can be calculated from the EMF equation of the DC generator. So this is the principle of the DC generator. Means according to Faraday's law of electromagnetic induction, whenever the current carrying conductor is placed in the rotating magnetic field or conductor will be rotate, then we are getting the induced EMF. That induced EMF is directly proportional to the rate of change of flux linkage in the coil, is called as a Faraday's law of electromagnetic induction. This is the principle of DC generator. Now, if the conductor is provided with a closed path, then the induced current will circulate within that path. So, in a DC generator, field coils will be produces an electromagnetic field and the armature conductors are rotated into the field. What I am saying here, armature conductors are rotating here and the field coils or magnetic field coils produces an electromagnetic field will be constant. So means which type of induced EMF you are getting here? Dynamically induced EMF I am getting here. Okay. So now an electromagnetically induced EMF is generated in the armature conductor. That direction of induced current is given by Fleming's right hand rule. In case of the DC generator, the direction of induced current is that depends on the Fleming's right hand rule. So this EMF will cause the current to flow if the conductor circuit is closed here. So hence most basic two essential parts of the generators are, one is the magnetic field. This magnetic field will be as a field coils that will be as a constant, and the another is the conductor which will be moves inside the magnetic field. So these two are the main two parts of the DC generator. We'll take one single loop generator here. You can observe here single loop generator according to the principle. We are considering here the rectangular loop of the conductor here. The rectangular loop is having A, B, C, D terminals. You can observe here. This is the A, B, C, D loop conductor, which is rotates inside the magnetic field about its axis A and as well as the B. So when the loop will be rotates from its vertical position to the horizontal position, so this is the vertical position. It moves from the horizontal position. Then it cuts the flux lines of the field like this. Okay. So means as during that moment, the two sides, that is AB and as well as the CD of the loop cuts the flux lines. There will be an EMF will be induced in this both of the sides, that is AB side as well as the BC side of the loop here. Okay. Now you can observe here. That is what I am saying. As the loop gets here closed, there will be a current will be circulating through this loop. Then current will be circulating through this loop. So the direction of current can be determined by Fleming's right hand rule. The current direction will be depends on the Fleming's right hand rule. So this rule will be says that if you stretch the thumb and as well as the index finger and as well as the middle finger of your right hand perpendicular to each other, means like this. So this is the thumb, this is the middle finger, this is the index finger of your right hand. If you are stretched like this, then these three fingers are perpendicular to each other here. Then thumbs indicates this thumbs will be indicates the direction of motion of the conductor. Direction of motion of the conductor. And index finger indicates the direction of the magnetic field. This index finger will be shows the direction of the magnetic field. And this will be direction of the current. This middle finger will be direction of the current here. So means that is the north pole to south pole. This here you can observe here in this space, this north pole to south pole. So, and the middle finger will be indicates here direction of flow of current through that conductor. So these three fingers I am putting here like this perpendicular to each other. So each finger indicates each one. Your middle finger will be indicates north pole to south pole, indicates the direction of the flow of current through the conductor here. Okay, now you can observe here. So this is the direction of the flux color and this is the direction of the current color. So this green color I am indicating here and this color will be indicated here. You can observe here. So this is the direction of the flux and this is the green colors. This is the direction of the current here and this is the direction of the rotation of the conductor from one place to one side to the another side. This is the what? Vertical side. This is the vertical side of the conductor. Now this is again at this position you can observe. I am again rotating here. So again this is the direction of flux here. At this position the tangential motion of the sides of the loop is parallel to the flux here. Is parallel to the flux lines of the field. Hence there will be no question of the flux cutting and consequently here there will be no current in this loop can compare to the previous loop. You can compare here. There is the current direction will be this current flow is there in this vertical position. But in this direction, there will be no question of the flux cutting here and consequently there will be no current in the loop. Okay. So now again I am rotating from this is the AB is the south pole side I am getting and the CD is the north pole side I am getting. If you are rotating again direction of the rotation of the conductor. Now again here presents the current here because here the tangential motion of the side of the loop is again perpendicular to the flux lines here. Again perpendicular to the flux lines here. Hence rate of flux cutting here maximum here. According to the Fleming's right hand rule, at this position current flows from where? B to A. Current flows from B to A and to another side from D to C here. In the previous first case one, that is the A to B and C to D. Here also the current direction will be reverse now here. That is B to A and C to D. D to C here. So now again here current according to the Fleming's right hand rule, the current will be flows from B to A and another side will be from D to C here. Now if the loop is continued to rotate about its axis here, every time, what I am saying here, every time the side AB comes in from front of the S pole and the current flows from A to B. Again if you are rotating, when it comes in from the north pole, that is AB side is coming to the from north pole, the current flows from B to A and similarly every time the side CD comes in front of the south pole, the current flows from C to D. When side CD comes in front of the north pole, then current flows from D to C here. According to the that is single loop conductor rotating in the magnetic field. Okay. So now if you observe this all phenomena, this all cases from case 1 to case 4, if you are observing that all cases, the phenomena is differently, we can conclude that each side of the loop comes in front of the north pole, the current will flow through that side in the same direction. That side in the same direction. And if you are goes to the another, that is from the north pole to south pole, that is down to the reverse plane. Down to the reverse plane. So similarly, each side of the loop in front of the south pole, the current through it flows in the same direction. So upwards from the reverse plane here. So when conductor is vertically positioned or parallel to the or perpendicular to the flux, then we are getting the maximum cutting of the flux. If parallel to the flux, there is no flux cutting of the conductor, means current flowing through conductor absolutely 0. So from according to this one, the topic of this, according to this all phenomena, the topic of the principle of DC generator is depends on the Faraday's law of electromagnetic induction. According to that one, whenever a current carrying conductor if you are placed in the magnetic field, then we are getting the induced EMF. That induced EMF is, in case of the DC generator, is dynamically induced EMF, because the conductor is rotating and the magnetic field is constant. So this is the working principle of DC generator. So another example I am giving here, can observe this also. So this is I am taking the single loop generator, that is again ABCD is connected to the one conductor here and segment here, and is 1 and 2 brushes is there I am taking here, 1 and 2 brushes I am taking here. Segments AB is rotating from one side to the another side. So this is also one example for working principle of DC generator. Okay, tomorrow we'll discuss on topic of construction of DC generator. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.